Alright, hey everyone, Nick here. Had a project I was working on a couple of months ago that didn't quite work out the way I was hoping, but I spent a lot of time and energy playing with it anyway, had some fun, and I thought I would go ahead and make a video about it and kind of get it off my plate. The idea, for whatever reason, was to create an electric slide rule. So what is a slide rule? It's an old mechanical computing system, right? So the easiest thing you can do with a slide rule is multiplication. And let's say you want to do 2 times 3. You come up here on the scale labeled A and you find the number 2. And this middle scale can move, right? It's just slides inside. So you take the end of that scale, which is this number 1, and you put it right underneath where the 2 is, like that. And then if you wanted to compute 2 times 3, you just slide this guide over the number 3, and where it's pointing on the top scale is the product, 6. And you know, for free, 2 times 4 is equal to 8. So there's the 4 and there's the 8. And 2 times 5 is equal to, well, it's not 1, it's equal to 10. It's the thing after 9. So this is 9, this is 10, and so on. So if I wanted to do 4 times 5, I would put my 1 here over right underneath the number 4, and then I would slide this over to the 5 on the bottom scale, and on the top scale I see the number 2, and it's not 2, right? This is 1 through 9, and then this is 10, 20, 30, 40, 50. So that's the basic function of a slide rule doing multiplication. And it's really not magic. What is this? This is just an adder, right? But what it's adding is logarithms. So if you take 2 rulers and you mark them off in, say, inches, you can do simple addition. So here's a pair of rulers, and I've got inches marked on here. And if I want to do, for example, 2 plus 5, I can find the number 2 on this first ruler, put the end of this ruler right here at the 2, and then if I go over to where the 5 is, I can look right above it, and there's a 7. So 2 plus 5 is equal to 7. We're just adding distances. Well, a slide rule adds distances, but those distances are not marked evenly. They're marked logarithmically. So when I come down here to a 2, and I come over to a 3, I'm adding this distance from 1 to 2 and this distance from 1 to 3, but those are actually logarithms of the distance. And so I'm adding logarithms, and if you write out the equations for this, when you add logarithms, you're actually doing multiplication of the thing whose logs you took. So all we're doing is, for example, if I want to multiply 2 by 3, I can take the log of 2, and I can add the log of 3, and I get this number, and if I take the anti-log, e to the x, that's equal to 6. So by adding distances on here, if those distances are actually logarithms of numbers, the distance I end up with is the logarithm of the product of those original numbers. So that's a mechanical slide rule. Why would you want an electric slide rule? You probably wouldn't. There's really no good reason for it. It was purely, you know, I had a little bit of spare time, and it was something to play with. Alright, so how are we going to make an electric version of this? My idea was, you know, let's just use a variable resistor, so a potentiometer, which is a resistor that we can change by turning this knob. So if we hook this up to a multimeter, this is a 5 kilo ohm, so we're on the kilo ohm resistance reading. This is a 5 kilo ohm resistor, and by turning this knob, we can change the resistance from 5 down to 0. And so my idea was, if I were to add up resistances and mark them on a scale logarithmically, right, it would be the same thing as adding distances on the wooden pieces of a mechanical slide rule. So all I needed was a circuit that could let me add resistances to be able to emulate multiplication and division. So let me show you the circuit for this, and I'll talk about the sort of horrifying realities that I ran into. The basic idea of the circuit is, let's just use an op amp. So basic op amp, this is a standard configuration for a non-inverting multiplier, right? So you put an input voltage into the positive side of the op amp. You have two resistors, R1 feedback from the output to the inverting input and R2 from the inverting to ground. And the behavior of this is the output voltage is a multiple of the input voltage. The multiple is 1 plus the ratio of those two resistances. So great, I can make a multiplication. Here is the idea. If I were to adjust R1 and R2 so that they were exactly the same resistance, the effect would be R1 over R2 is 1. My output would be twice my input. So this would be a voltage doubler precisely when my two resistances are equal. So that led to this idea of let's go ahead and make a circuit with an op amp, and it looks like this. So this is just power coming in from a USB port. I'm going to get a 3.3 volt regulator, so I get a very precise 3.3 volts, and we're going to trim that down through a precision trimmer, so a very fine tunable potentiometer, to 1.25 volts, 1.25 volts going into here. This is just a voltage follower that insulates the input from the output. So now I have 1.25 volts going into the top of my circuit. So this is 1.25 volts going in the top. And then a set of resistors. So I have resistor A and B over here between ground and my inverting input. So that's this resistor R2 is A plus B plus an extra 1 kilo ohm. We'll see why in a minute. And R1, the feedback resistor, is another potentiometer X plus 2K. And I dialed this in to be precisely 2K. And so what does this mean? So, oh, and then the output also goes to a voltmeter. So this is a 5 volt voltmeter that measures, between 0 and 5 volts. So the idea was R1 is my output potentiometer plus 1K plus another 2K, right? Because we've got our output X, and we've got an extra 2K, and I'm always going to add 1K to these potentiometers for reasons I'll talk about in a minute. And then R2 is going to be my A potentiometer plus a K, B potentiometer plus a K, plus an extra 1K over here, right there. And so my total resistances are A plus B plus 3K and X plus 3K. And those will be equal when A plus B is equal to X. Alright, so all of that's just a long-winded way of saying, the way I've got this set up, if A and B, those resistances add up to X, then I should get a 2X multiplier out of this op amp. I got 1.25 volts going in, I should get 2.5 volts going out. So an output of 2.5 volts will tell me exactly when this resistance X is equal to the sum of these two resistances A1 and B1. And my output meter looks like this. I've got 0 volts over here, I've got 5 volts over here, so 2.5 volts should be exactly in the middle position when this thing is straight up and down. And so here's a little box I built that has exactly this setup. So a set of input dials A and B and an output dial X. Okay, so here's why I'm messing around with adding an extra 1K. The first realization I had was that these potentiometers are not exactly as advertised. So this 5K potentiometer, as you may have noticed, when I turn it all the way to one end, it's 0. When I turn it to the other end, it's not actually 5K. It's 4.94K. So to deal with that, I'm not going to take it all the way to that extreme position. I'm going to call it fully on when I'm somewhere shy of that position. But the other thing I discovered is that these things are not linear. So if I put it halfway between all the way off and all the way on, it may not be halfway between 0 and 5K. And in particular, the linearity is really bad at the extremes. So if you look at graphs from the manufacturer on these things, what you find is that, you know, your ideal would be your resistance changes with position, but in fact it's something like this. And so in the beginning, when you first start turning it, and at the end, when you're close to the end, the change in resistance is much flatter. But it's linear in the middle, say 80 or 90%. So I decided, instead of going from 0 degrees to all the way turned, I would ignore the first 10% or so of the rotation, and I would ignore the last 10% or so. So this potentiometer over here will turn all the way over to that position, but that's not where my dial begins. My dial begins right here with the number 1. And it will turn all the way over to this position, but my dial ends right here with the number 100. And so the full range that I'm considering for this potentiometer is from here down to here, with the hopes that I would be using this variable resistor mostly in the region where the change in resistance is linear, right? So it's got a linear relationship with the position of this. And so I made measurements of 3 potentiometers and recorded at each angle what the percentage of the full resistance was, percentage divided by 10, just an arbitrary scale. So so came up with those, and then used that along with some code for drawing some lines in circles based on starting and ending angle, to come up with these dial markings. These dial markings are not the same, right? For example, the 100 over here is much further along the curvature than this 100 over here, because this one had a different performance curve from these two. But using that, I tried to set these up so that they would correspond to a nice predictable linear relationship. So the goal was that this would be 1K over here. So anyway, I built this up. It's a very simple circuit. It's mostly one op amp. There's a 3.3 volt regulator with a heat sink sticking out of the top. There's some trim pots and some connections to the potentiometers. There's my USB power, and I did not, seal this thing up because it was still a work in progress. But to explore its behavior, so we can start off, we can put this dial at 1, this dial at 1, and this dial at 1, and our meter is centered. So this blue line underneath the dial represents 2.5 volts. And so if you want to do arithmetic, basically what you do is you turn this first dial. So let's turn this to the number 2, and you have to look at it head on, so that's a little tricky to do with this angle. And then we turn this dial to 3, and then we turn this dial until that needle is nicely centered, and it looks like right about there. And if you look at where this is pointing, it's pointing at the number 6, and so 2 times 3 is 6. And if you want to do 2 times 2, you point this one at a 2, point the first one at 2, and turn this until the needle is centered, and there it is, and it's pointing to 4. So 2 times 2 is 4. So all you're doing here is setting these two to the logarithm of the amount of rotation, which is marked off in these face plates, and these resistances get added, and then you turn this until your output is 2.5 volts. And by design of that circuit, the output will be 2.5 volts when this resistance is equal to the sum of these two resistances. And the markings on this will tell you the number whose logarithm corresponds to that amount of rotation. So that's the simple electric slide rule setup. Biggest problem is the nonlinearity, though, right? It is dialed in a little better than if I just use the full range, but it's still got a lot of error in there. The secondary issue is, you know, even if you're looking directly head on, is this a 2 or is that a 2 or is that a 2? Trying to dial this in exactly, especially when you get further out here where the distances between these numbers is so much smaller, is really hard to do. So I really needed, you know, a much bigger dial, something, you know, a few inches across, and then a longer pointer on this see-through plastic that I could really dial in very precisely. Unfortunately, my sense was that if I did that, it would only highlight the inaccuracies of the potentiometers even further. But anyway, I got to play with an op amp, and I got to do a little soldering, which is always fun after doing a lot of breadboarding, and and I got to 3D print what I thought was a pretty cool looking case. So that was an experiment. Didn't really work out with the fidelity that I was hoping, but interesting stuff to play with in there anyway. All right, that's my electric slide rule. Thanks. Catch you next time. Bye.